Okay. Do you hear me?
Yes, yes.
Okay. I start to introduce my group. Maybe Emanuele and Giulio are already there, so when I call them, maybe they can say hello. My name is Francesco Brigoli. I am a professor of seismology at University of Pisa, and mainly my background is in geophysics. I graduated at University of Pisa with a master's degree in 2010. Then I got a PhD at GFZ in seismology. Then after a couple of years at ETH, I spent 6 months in Stanford as a visiting researcher, and I got a JSPS fellowship as a visiting professor at University of Kyoto last year. Um, and actually, I'm mainly working with induced seismicity and photonic seismology, so mainly DAS, and developing machine learning techniques for seismic data analysis, essentially. My group is composed by myself, Emanuele, which is here. Oh, I saw him a few moments ago, and which is a postdoc with me, working on development and location method for using DAS data acquisition technology. And then we have 4 PhD students: Giacomo Rapagnani, which works mainly on moment tensor inversion using both conventional seismic data and DAS. And Giulio Pascucci, which should be also here, is now at ETH Zurich as a visiting researcher, and is working mainly on the development of the noising techniques for DAS data. And then we have other 2 PhD students that will work also on seismic source characterization using DAS data. Our research facilities generally are composed by seismic station. We are coming soon. We will acquire a new DAS interrogator, a Solgeo DAS interrogator. Is manufactured in Italy, and it's essentially low cost with respect to the others. And we have computational facilities. We mainly work in AI for seismology, so developing AI techniques to analyze massive seismic data sets. Photonic seismology as the things that we will show today, and also reduce seismicity topics like CCS, or now we are doing the monitoring of the ENI site in Ravenna, CCS site in Italy, in offshore Ravenna, with DAS, actually, with a fiber optic cable deployed in the injection well, and working on EGS, so enhanced geothermal systems. We also develop classic methods for working for the analysis of conventional seismic data, and with volcanoseismology sometimes. We are also involved in a project for the building of the Einstein telescope, which is a next generation gravitational wave detector, and the site characterization of one of the potential sites that will host the Einstein telescope is in Italy, and we are essentially doing the seismic noise analysis and modeling to see if this site is suitable to host the Einstein telescope or not. And so on. This is my group mainly, and our activities. And now I can start directly with the topic of the talk. If you have questions, I will be happy to answer now.
Is there any question? I think no questions for now.
Okay, perfect. So now I'm going to introduce one of our first work that was already published, and and also the ongoing works, how to improve waveform-based detector using AI. Was initially our University of Pisa project, and then become with Total. We just joined the forces to improve this detection using AI methods. So it's a collaboration between University of Pisa Seismic, which is a spin-off of the University of Pisa, which works mainly on multi-seismic monitoring, and also Total Energies. The application, before to start directly with the methodology, I will introduce the data set that I will show for for the that for which we will apply the methods. Essentially is one of the most known public data set, fiber optic data set, DAS data, public DAS data set available, which is the UTA4 EGS dataset, which is essentially an EGS project where they deploy the fiber optic cable in two monitoring well, and they performed hydraulic stimulation in order to create an enhanced geothermal reservoir. We decided to use this dataset because generally we were interested at the beginning of our application to work with wells, so with us deployed in wells. So we thought this was the best available data set at that time. However, our approach was then extended to also surface dust data, and now we have a set of tools that allow to more or less to analyze any configuration with any fiber configuration. So, how the method works? The methods essentially is a semblance-based method that probably you know from reflection seismics. It's We borrowed the concept of coherence estimation using semblance, and applied it to DAS data. How the method works essentially? The methods consist in defining a set of hyperbolic trajectories, which are not, while in reflection seismics, these hyperbolic trajectory are related to seismic velocity because you generally have the position of the source. So the vertex, the curvature of the parabola depends on the stacking velocity. In this case, the dependency is more complex. So in order to remove any dependency on the velocity and location of the source, because we don't know the location of the source, we will calculate only the curvature in terms of geometry. So it's the geometry, the curvature of the hyperbolas are pre-computed by only taking in consideration geometrical aspects. And so once we pre-calculate the hyperbola for different curvature and different, of course, also vertex position, what we do is we transform our data, our raw dust data, into stacking function. We apply different stacking function. There would be a paper that will be released in few weeks that was just accepted. But essentially, what we apply, it could be a combination of hyperbolic cosine functions or energy or STA, depending on the nature of data that we would like, the envelope, on the nature of data that we would like to acquire, on the noise condition, and so on. So how the method works? The methods can be described with a series of sketches that better represent the workflow. So as I said before, we pre-compute different hyperbolic trajectories, and we also scan different vertex position, the different vertex position for the hyperbolic trajectory, and we we stack all the data along each possible trajectory, each possible hyperbolic trajectory. We do this for all the times along the trace. After that, we finished this process for each sample. We extract the coherence value for that correspond to the we extract the curvature and and the vertex hyperbola that corresponds with the maximum coherence value. So we extract the maximum coherence values for each different curvature coefficient and for each different vertex position. Produces essentially a multidimensional matrix whose projection will be like this. We will have a a coherence function. Here we are just representing the curvature coefficient and the time, and we have the maximum. The maximum of coherence corresponds with essentially with the location with the events. So if we transform this coherence function into a time series, so for each of these for each curvature, we extract again the maximum of the coherence along this line, along all the vertical lines. What we get is a time series that that contain only the maximum coherence values. So what we see here, this is the coherence values across the time, and when we have a sharp increase in coherence, it means that we have a seismic event. We have also a clustering algorithm that allow us to identify if an event is really an event or not. There are few parameters that needs. So if we have just a sharp peak because we have some spike in our data, the clustering algorithm will recognize that this is not a true event. It's only it's a false event. So we set a threshold that generally it's tuned depending on the data set and the application. When we get when the current value is above a certain threshold, what we do, the clustering algorithm will check if there are contiguous maximum that are above the threshold and detect the seismic events. This is a real seismic event from 3 seismic events from the forged dataset, and you see that the detector was able to detect correctly all the three seismic events within the time window. We applied this approach to the first simulation occurred in 2018, if I remember correctly. No, 2021, sorry, in April 2021. And we compared the catalog we obtained with our detector with the catalog obtained by Silixa. Silixa essentially during the first simulation also the well was cabled with engineered fiber, a constellation fiber, and they used also the Carina sensing system, and Silixa itself analyzed the data. They detected essentially nearly 1,000 events. So, and what we did essentially is comparing our catalog with the Silixa one. What we obtain is that we not only detected almost all the detection that Silixa got, that Silixa got more or less 1,169 events. We detect from this pool we had a common 1,100 common detection, and actually the 1,086 common detection, and we missed only 83 events from Silixa catalog. But we detected 1,100 more events with respect to Silixa. So we doubled the number of events with respect to the Silixa catalog. And we checked manually all the events, all these events, and what we obtain is that only 70 events from only about 100 events were events that are ambiguous. I mean, events that could be or not. We are not sure if it's noise or not. Let's call false detection. While in the Silixa catalog, from the 83 catalog, that from the 83 events that we missed, 70 are false detection. So essentially, we only missed 13 events, but we get 1,000 more events with respect to Silixa. And this has shown that this approach was applied to other data set, and like Kefalonia, maybe Emanuele will show something in the next presentation, shown that this approach works very well for to detect seismic events. Actually, in order to this is for instance two events that we detected while Silixa was not able to detect. Uh, Actually, since the method was quite promising, and we wanted to make it faster and also less dependent on threshold that you have to set in order to identify an events, we tried considering with experience that we obtained with another work with conventional seismic dataset, we tried to work with classifier, a convolution neural network. Essentially, what we do here is we calculate the semblance for our rows, for our dust data. We transform the dust data in a semblance panel. So after applying the semblance, what we will get is an image that contain the coherence values. And instead of then extract a maximum for each time, what we do is just using a convolution neural network to recognize if the image, the coherence image correspond to a true event, or it's just noise. And this is the convolution neural network. The advantage of this approach is that it can be trained with synthetics. You don't need the real data to train this convolution neural network, because it's very easy to reproduce the pattern of the semblance. It's essentially the semblance is a simplified image of the real dust data, and this makes the comparison between synthetics and real much easier. And for this reason, it's easier to it works very well if we train the convolution neural network, actually the residual network, with a residual convolution neural network with the synthetic data, and then apply directly the real data for the detection. So this classifier tell us for each data window if that window contain an event or not. So As I said before, what we have done in order to train our approach is our convolution neural network uh, is creating synthetics. In order to create synthetics that are very similar with real data, we use the spectral element model, a spectral element method, which is called the software is called Salvos, that allow directly to simulate the fiber, simulate the wave field and return as output directly what you will expect that will be recorded from a fiber optic cable. And you see here we still for Forge. This is the real data of Forge, and this is our synthetic data. You can see that the synthetic data is in some ways is very similar to the real data, and allow us to use this kind of data, apply the semblance, and make it very and successfully apply the convolutional neural network for classification. Let's see how this method works. Here we are showing the training dataset. We are applying as a characteristic function the STA LTA of the hyperbolic cosine, and which is essentially a characteristic function that enhance the energy, but retaining also the polarity. It's the derivative of STA of the hyperbolic cosine. And this is an event, and this is for a very short, this is only a few seconds of, um, and this is the semblance panel that we will use for training. From this, we get this essentially, and we use this to train our dataset. This is noise. So this is what we get for a small window of noise, and this is how the semblance panel will look like when we encounter noise. So let's see how once we train our convolutional neural network, let's see how the detection now works. For each small window, let's say less than 0.5 seconds of window, we extract this data, we calculate the semblance, and the classifier, so the convolutional network, will tell us that this is noise. Here that we have noise, and here we have also noise. Here we have noise. Here we have an event. You see here, so it automatically recognizes an event. Here, it's still an event because there is part of the event still recognize that there is something, but the score decreases. The noise score here from 0 increases to 0.4, while the event score decreases to 0.6. So it's essentially the coda of and it continues until it scan and all our data set. So let's see some results. We tested this approach with the with the same data set that with the 2022 data set, a new stimulation, and but only for 20 minutes because this is an ongoing work where we need to apply to a larger data set at the moment. So this is only preliminary results. But you can see here that here you have an event, you have something here. So at some point you have an increase, but one of the event is here, and automatically the classifier recognizes that there is an event. The same here. These are detections that are in the Silixa catalog, and we also spotted. Here the same, so we have an event. And also here, this is quite interesting case because we have two very close events. So there are two events that are very close each other in terms of time, and the detector is able to spot them. In the classical detector would essentially got only one event, mainly because with the clustering, what it will probably it will have only recognized a single event instead of the two. So this is quite interesting results. And also, even if for smaller events, it's able to correctly. This is a small event. Even in this case, it's able to correctly recognize the events. Here, you see, this is an event that is smaller, and we have an increase, but it's let's say ambiguous for the detector. Here we have still two other events, and these are new detection. These events were not detected where we detected these events, but these events were not present in Silixa catalogs. This is also a new detection that was another event that was not present in the Silixa catalog, and we were able to spot it. And also this. So at the end, what you obtain, this is our other detections. Here probably there is a small event, but we missed it. And here we are also in an ambiguous, let's say, it's ambiguous for the detector is struggling to understand if it's giving more or less half and half probability that this is an event or not, but actually this is an event. So this is, for instance, one common detection, one the largest event. What we have done essentially is we applied this machine learning, let's say, version of the semblance-based approach, semblance detector for DAS data on 20 minutes of forged dataset of the stimulation of the 2022. And we set as a threshold for event a probability of 0.4. What we did essentially, we identified in the Silixa in this 20 minutes, Silixa catalog contains 39 events, and we identify all these 39 events with our approach, plus other 37 events that we manually inspected. From these 37 events, 28 events were true events, while 9 events were false detection. So essentially, we got um, also in this case, we almost doubled the Silixa catalog with 28 more detection with respect to classical one. So essentially, the conclusion of this work is that semblance-based algorithm for detection works very well, even if used with a classical approach. But the machine learning detector allows us to remove and have more control on few parameters that need to be tuned and generally are application specific. This approach this approach exploit the high spatial density sampling of DAS data, and it's and for this reason the results with respect to standard seismological techniques are much better. We obtain much better performance with respect to standard seismological techniques. And the main advantages of the machine learning version of the detector is that we can train our machine learning model directly on synthetics. So this means that we don't need real label data that sometimes we don't have because we just install a fiber, we start to record, and we don't have already a catalog. In this way, we can create in advance a synthetic dataset, maybe use few hours of noise to simulate to better have noise instances that and train with the real noise. But for the synthetic events, we don't need for the seismic events, we don't need the real data. We can use the synthetics. It's the main what we have to improve is that the computation of the coherence is demanding for long fibers. So for fibers that are that have a length higher than 10 kilometers, it become hard. So we need a lot of computing. It's more computational intensive. And we can improve, of course, our generation of synthetics using more advanced techniques for simulating, for instance, noise. And maybe also trying other characteristic function, like the one that, for instance, Giulio is using, which is Tekeo, which probably he will present later, and explore other coherence functional. This is what we are doing now to improve the methodology. Thank you. And here you have in this QR code, it's the submitted version of the work, the classifier that was applied to conventional seismic dataset. The machine learning seismic data classifier that was applied at the moment with the conventional seismic dataset. Thank you.
So for the questions, I'll go ahead and ask those who are here in person, and then I'll come to those who are online.
Okay.
Okay. Thank you, Professor. Actually, I'm Ibon by name. I'm an MSc student here in UTP. To be specific, I'm from the Department of Geoscience. So I'm also working on DAS dataset. So my first question goes thus: like these model you just developed, the DL seismic detection for DAS. So is it very suitable or going to be efficient if it is used on passive DAS data? I'm talking about the ambient noise data. So that's the first question. And the second question, and I have actually it doesn't based on what you just discussed with us now. So that's to do with ambient noise data itself. Like and I have to like ask if at all this DL seismic detection method can as well work for ambient noise data, the passive data itself. So let me stop here. Actually, I have another question also. Maybe you should go ahead and answer that.
Okay. Can I answer or wait to the other question? No. For ambient noise, no. It's this approach works only with microseismicity, so events that are earthquakes, micro earthquakes or earthquakes. Of course, for ambient noise, it's no. It's I would say that it will not work because it's not the scope of the. So what we will our aim is to catch earthquakes, to detect seismic events. We don't work too much with ambient noise, so we never work tested for that. Uh, so no, we don't know if it could be applied. I don't know exactly how it can be applied because this is a detector that identify microseismic events. For the ambient noise, probably you mean for imaging using maybe like the semblance like in the reflection seismics could be. I don't know, but yes, we never tested.
Thank you. So, I'm Josh. I'm a seismic interpreter. So I started working with volume seismic data sets. So I have been working with offices, metrophysics, seismic attributes. So while during my research, I discovered some Python libraries like GASP, like a number for multi-variable programming, like all of these for plotting of multiple data points, billions of data points. So I decided to apply that in my project. Okay. So now my question is, you said emphatically that your model, your machine learning models, or I know it's deep learning models, they take your seismic data directly and they produce efficient results. So I'm more keen on how did you go through the physics-based, is it physics-based, or how did you go about the data processing? Because the models can't just take the data with the noise and then produce the results directly. So I want to know how you do the magic. Thank you.
Okay, so essentially the machine learning model itself, it's trained. So let's suppose here you see my screen still. So what we do essentially is this. We try to generate the model that best resemble the real data. So this is a real data. So we generate a synthetic data that has the best that is has the most similar features with the real data. So we need to use, of course, advanced simulation algorithms, like for instance, Albus for simulating wave field and having the dust data, the synthetic dust data. We simulate the noise, but using realistic noise condition, which means we extract real noise, few hours of real noise, and we stochastically using the spectral property of the noise, we simulate stochastically the noise in order that we can have many instances of noise for the training. Then this is not the data. This is the data that we will use for training, but will not use directly this data for training, but we will transform the synthetic data by applying the semblance into a coherence image. This coherence image essentially it's a simplified version of the original data, because we are just mapping the data from one domain to another domain. In this case, from xt domain, x is the axis of the fiber, t is time, into another domain which is that is coherence versus time and other parameters, like for instance in this case curvature coefficient, but could be also the vertex parameter. So this is what we will use for training. Of course, we can apply a denoiser, but if you follow a processing sequence for the real data, we have to follow the same processing sequence for the synthetic data, because this is just to maintain the coherence in terms of processing steps. So let's suppose if we generally, before to apply the coherence, we remove the K0, we apply a FK filter removing the K0. This will be applied both to the synthetic data and to real data before to apply the coherence, in order that you have some sort of consistency in the data processing.
Okay, thank you very much. Any other questions?
No? Okay. My name is Adwan, and I just want to ask some question, because you know that just can only record for a single component. When compared with if we are using is there any limitation when we are doing the microseismic monitoring, when we are using that compared to the conventional geophone?
Sorry, can you repeat the question? I didn't get.
Right now, we know that that can only measure a single component. So
Yes.
okay. So compared to conventional geophone, which can do like 3 components, is there any limitation when we record the microseismic data?
Sure. Good question. Yes, in principle, for instance, if you deploy a DAT in a vertical well, you cannot locate events because it's a single component. So you have an azimuthal ambiguity. While with three-component geophones, yes, you have the possibility to use polarization analysis and locate events. This is one of the limitations, of course. We developed some techniques that allow us also to locate events in vertical well. But of course, the limitation DAS is like a 1D component. But the main advantage of DAS is the high channel density that allow you to have, for instance, information about the wave field that with sparse network you can't. For instance, this is the S, and this is P S converted. P converted to S, S converted to P, sorry. And this information can be used for imaging, or because at this interface, the S is converted to P, sorry. And you can use this information to have better models for imaging, but also for location, for instance, if you can model these phases. And this is it's almost impossible with sparse networks. So at the end, yes, maybe DAS it's a single channel. It's like a one component, so it's does not allow you to have the other components. But on the other side, the high density spatial density of channels at the end have a better advantages that with respect few sparse geophones, unless you are not you are using thousands and thousands of nodes. In that way, maybe it could be different.
Thank you very much. Is there any other question? Last question. Last question.
Thank you, Professor, once again. So when you are mentioning about your belt tours the other time, so it's like you're also working on inversion. So like this problem I'm currently facing on doing inversion for kind of ambient noise event, because in a scenario whereby we are working on ambient noise data, so we so call the ambient noise the data itself, whereas all other events are to be categorized as noise. So now I've reached to a stage where I have to estimate the dispersion curves. So I have the sort of dispersion curves of which I've actualized, the fundamental mode and the overtones. So now I have issue with the mode casing. So I want you to suggest, or let's say, give me advice on what to do in order to separate the fundamental mode from the overtones.
It's I think you are applying your DAS data with ambient noise extract dispersion curves, I suppose.
Yes, actually, I decided to just jump to the conclusion because there are a lot of process steps you have to follow. Then to the later part, you do the cross correlation. So I just decided to just jump to the dispersion part. So
there are, I think, I don't do imaging, but I think there is a group at ETH that is working on ambient noise imaging using full waveform inversion directly, not directly the dispersion curves or the dispersion. So it's working directly on the waveforms. It's full waveform inversion for ambient noise, but it's a group at ETH. It's not my group that is working. We are not doing imaging with us.
Please, those online, do you have any question?
Okay, thank you. I think I can stop sharing and we can move to the other.
This presenter is Dr. Emmanuel from University of Pisa.
So yes, are you able to see my screen right now?
Yes, we can.
Should be a okay PowerPoint presentation. So let's start. Okay, so Everything fine, no? Can you confirm it? Very good. Let me, okay, put this. So, as Francesco already mentioned, I'm a postdoc at the Department of Earth Sciences, University of Pisa, and right now I'm working on DAS for earthquake location. And today I will show you two tools, which are called Lion and Orion, for earthquake location with integrated seismic networks. So, first of all, let's give it a background on these integrated networks. What I mean is the next generation seismic monitoring infrastructure, which combine both the existing conventional networks, which are often sparse with tens to hundreds of sensors, with both horizontal and possibly in well data from DAS or DTS if you have wells, which are extremely different from the sparse sensor, because they are distributed sensor for the horizontal part, which with often complex data, given the fact that you have uniaxial sensitivity and also the problem of the coupling with the ground. And for the vertical, for the data in wells, you typically have higher signal quality, but as Francesco already mentioned, typically poor azimuthal coverage. So this is the context of the research. So just to give you, again, a bit of background, this is a typical DAS data from a surface experiment. These are data from an experiment in Greece, in Kefalonia Highlands. And as you can see, 20 seconds of data, you see clearly see two events along a 15-kilometer long fiber optic cable. So this is basically how typically DAS data from surface experiments appear. Of course, there are, in this case, with a 2-meter channel spacing, more than 7,000 channels, so an extreme data density, spatial density, but also strong spatial variability in signal quality. Just focus on the left part of this slide, where you can see clearly, since those traces are normalized trace by trace, you clearly see the saturation from cars, given the fact that this part is on land, while in the central and right part of this slide, you clearly see spatial variability in both P and S phases, coming from the fact that basically the center part, sorry, I forgot to put a marker, but it's basically the center part of this slide. There's a transition between the terrestrial part of the cable and the offshore marine part of the cable. So you clearly see strong spatial variability in signal quality, given the fact that you have variabilities in the coupling with the ground, and also some strong reverberations in this on the right part of this slide in correspondence with the deeper part of the on the marine section. So the question is, so the research question I'm trying to answer during my postdoc is how to efficiently integrate those very dense data into the often sparser existing seismic monitoring infrastructure. So typically the problem is this one. So you have DAS data here on the left, which are typically more than 1,000 of individual observations, so DAS channels, which should be merged with sparser and three. DAS, of course, as Francesco already mentioned, one single component, and to be merged with 3 components sparser data from conventional seismic networks on the surface. So that's the problem. So basically, it's 2 different data sets, both in terms of signal quality and in terms of data abundance. So the challenges for an efficient integration is, First of all, the features, the dust data features. So how to handle this extreme spatial and temporal variation in signal quality in near real time, given the fact that you have high data volumes, and in coming from this problem, how to select good quality data from the subsequent integration into the sparser network. Because, as I mentioned, from let's say tens or hundreds of sparser sensors, you want to add the data from thousands of channels from those experiments. So to guarantee a one-to-one integration and thus avoid biases in source characterization, you want to there are typically different way of to be explored, either data selection or data weighting. What we are exploring right now is data selection. So to focus on the source location problem, so the existing conventional network typically ensure the azimuthal coverage, because you have sensors that try to maximize the coverage on length of a monitoring area, or a monitored area, while with horizontal and in-well fiber optic cables, you typically have data closer to target epicenter or in the wells to target hypocenters. But as I mentioned before, with typically poor azimuthal coverage, or let's say at least compared to the conventional network. So as data from the fibers can add constraint to the solution and bridge observational gap, just think about those optical fibers interrogated, those oceanic optical fibers that can be interrogated from land and can add data closer to the actual epicenters if the epicenters are on offshore. But often they come with a drawback, so a poor user control given the data density, and which typically result in offline analysis, in a dominance on offline analysis, or basically moving towards away from a near real-time application, and potential bias in the solution given the fact that you have an unbalanced number of sensors, so tens or hundreds versus thousands, as I mentioned before. Right now, what we are testing is waveforms, is event location by waveform stacking, and so which bypass the picking step and exploit waveform coherence. And however, like the volume of data in this case can hugely impact the computational efficient, and also the efficiency in the effectiveness on in the grid search approaches. So, okay, so the goals we are working right now is to have a tool which is efficient, so it's a waveform-based, waveform stacking-based locator, which is able to manage very dense dust data, so the computational costs. It's able to separate the contributions, giving three different let's say, coherence maps from the conventional network, from the optical sensor network, and from the integrated network. And it's able to give in the integrated network case, to give a balanced solution. So a balance between dust and seismometer. So those are the goals for a waveform stacking based locator with integrated networks. So about the efficiency, what we are working right now, and we already tested, is instead of using, in this case, at least for dust, thousands of 3D travel times lookup tables to extract travel times, which are synthetic travel times, which are used in a grid search to build those coherence maps, to instead use a single 2D travel times table spanning the whole location domain, of course with an approximation of a 1D velocity model, but still reducing the need to, let's say, use those thousands of 3D travel time lookup tables, but still able to provide a 3D coherence map for event location. About the separational contribution, so the capability of providing coherence, as I said before, coherence maps for the conventional network, for the optical fiber network, and from the hybrid network. And about the balance, what we are exploring right now are two different approaches. So either use a selection of dust channels, which requires, as I said before, to go towards near real-time and automatic selection procedures, or a posteriori merge of the dust coherence map and the conventional network coherence map. So for these goals, for the automatic dust channel selection, we developed an algorithm called Orion, which is basically working in two steps. So first of all, it's geometry. In the first step is geometry driven, because it exploits the azimuthal information of the fiber, of the optical fiber, and the spatial contiguity of the channels to cluster the different sections along the cable, featuring similar geometrical features. And then in a second step, within those cluster, select, given from using a waveform attribute driven approach, good quality dust channels. So this is a work which has been submitted to GRL. So practically those two steps, this is a sketch. So basically you have this complex fiber optic cable, both on land and offshore. You use the first step, so you basically cluster the cable in a section with similar geometrical features, using both the azimuth information and the let's say the spatial contiguity of channels, meaning the fact that you don't want only to have section with similar azimuth, but with similar azimuth and be contiguous. So basically, from a single fiber optic cable, you select different sections with similar geometrical attributes, and within those sections, you select, given a data attribute score, good quality channels. So we tested the algorithm on several geometries, several real world geometries, and it seems working let's say quite well, because basically we are able to identify cable section with similar geometrical attributes, but of course with cables which show poor azimuth variation, we also added the possibility to add subsections within those very long sections of the cable to have to ensure spatial coverage, which is very important if you want to use those data for instance, for event location. So this was the test on different cable geometries, but also, and the resulting selected channels are shown in this slide. So basically the algorithm works in two ways. You can either put a threshold on the maximum number of output selected traces, in this case 50 channels, or you can give the algorithm based on the waveform attribute, let's say the degree of the freedom of selecting data from within the cable subsection. So here, as I wanted a fixed number of channels to be merged with subsequent data from a conventional network, I put the threshold to 50 channels. But the thresholds can be put to 10, to 100, or let's say about to put the threshold, and just select the one best channel for each section or subsection. So already tested this algorithm also on data from synthetic data. This is a salvo simulation, so a full waveform simulation with the added noise to let's say test if the algorithm was avoiding those noise sections and select data from the noise-free section. It seems working quite well. In this case, the threshold was put to 10 channels to be selected. And as a real data application, I used the Kefalonia dataset I mentioned at the beginning of this talk. So to give a context, basically, it's a 15-kilometer cable in Greece connecting the Kefalonia and Ithaca Islands with two, let's say, two on-land sections in the Kefalonia and Ithaca Islands, connected by a marine section with which shows, let's say, since the on-land sections are follow ordinary streets, they show, let's say, quite strong azimuthal variation, and that's why you basically with the step one of Orion you select, you find basically several subsections. Why in the marine section you isolate with just one section, because the azimuthal variation is on a number of channels which is above the number of channels you use to stack the signal. So basically these are the frequency of the selected channels along the cable, and as you can see, you have a practically an homogeneous selection of channels, which is good, because what we need from this cable is ensure at best the azimuthal coverage for subsequent event location, and that's what we tested. So basically we compared the we relocate a seismic sequence using DAS-only data with DAS-only data selected with the approach we are developing, so Orion, and a typically uniform selection of channels along the cable. And we show that the seismic sequence, the cluster of seismicity, the correct seismic cluster of seismicity is northwest of Kefalonia Island, and with the uniform selection, you have multiple mislocated events closer to the fiber optic cable, while with Orion selected channels, you end up with the vast majority. Even here with the histogram, you can see the distance from the catalog, which is an high quality catalog from the same area, not only with DAS. So with the Orion, you end up having more events, the vast majority in the correct and not position close to the seismic cluster and not mislocated closer to the DAS cable. And merging those two tools, so Lion and Orion, in the same workflow, we were able to locate events with the local network of stations, with the fiber optic network, with selected data from using Orion, and with the hybrid network, with the two approaches. So with the integrated network, so the data from the selected channels with Orion and from the seismic network, and merging the two coherence maps. So just to conclude, those two tools, so Lion and Orion, provide an adaptable event location with integrated network. So our goal is try to let's say allow efficiency with hybrid networks for event location through an automatic DAS channel selection and automatic integration with the local network of seismometer, without using AI or any peaking algorithm, because as I mentioned before, this is fully exploiting waveforms. So characteristics function estimated on waveforms. So if you have a question, I'm here and happy to answer.
before that presentation. Can you go to your section where you show the Cefalonia subsurface image?
The Cefalonia data, you mean?
Yeah, where you show this one. Okay. So the source of this data is microseismic.
No, those are earthquakes from basically it's a seismic,
No,
natural seismic sequence.
Subsurface images now. If you go back, the subsurface image. This one, yeah. So this is microseismic data. I'm wondering how did you get this? This is a subsurface image, is it?
No, those are, yeah. I mean, it
looks like subsurface.
Exactly.
Image,
I mean,
but they're not.
Given the fact that with us you have these, these beautiful images of basically the wave field, the seismic wave field traveling and passing through the complete length of the fiber cable, you end up with images that seems to resemble a seismic image. But these are, I forgot to put at the beginning of the slide, I put the axis, but basically on the x-axis you have space along the fiber, okay, and time on the vertical axis. So yeah. But I mean, those are more than 7,000 channels. So more than 7,000 seismograms, basically. And for our goals, we wanted to select a subset of channels to go towards near real time. But as Francesco mentioned, though the possibility with us, given the fact that you have this extreme spatial sampling, is to use not only the, let's say, conventional PNS phases, but also additional phases that you can clearly see with us to better constrain source properties.
Those online, do you have any questions? That's all. Thank you very much, Dr. Emmanuel.
Welcome.
Our next presenter is Mr. Julio, a PhD student from University of Pisa.
Stop sharing.
I'm sharing my screen. Can you see in presentation mode?
Yes, we can see.
Yes.
Perfect. So let me. Okay. So I will introduce myself very briefly. I'm Giulio Pascucci. I'm just started my second year PhD at University of Pisa in Italy, and I'm currently, as Francesco mentioned, an ETH as a visiting PhD researcher, and basically I'm working mainly on denoising methods, development of new methodologies for signal enhancement and denoising dust data, and I'm currently working on near real-time dust data denoising and signal enhancement methods. And today I will present you this work that I just, the paper of this work was just accepted, so hopefully it will be out soon. And it was my first work that I did on denoising dust data with a spectral subtraction based approach. So the motivation of this talk is actually why denoising is important. Of course, I'm also coming from the world of the reflection seismic a bit, so I know how much is important. Data denoising, seismic data denoising in general. So why this is important for actually for dust data? This is an example from the Utah Forge site, AGS site that Francesco already, the Professor Grigoli already shown previously. You can see on the left, this is just 1 second of data, but I mean, I challenge you to see, do you actually see something that is not noise? Well, if you look closely, probably here you can see something which, I mean, could resemble a seismic event, a microseismic event. But still, it's very hard to see and to look at if you don't do any, let's say, pre-processing steps. So, as Professor Grigoli has presented earlier, I mean, you could try applying the microseismic event detector, but in these cases, it's often a limitation. I mean, if you don't do any denoising. So, yeah, so this is just a comparison between a DAS channel and a geophone extracted from the same depth. Here we still in Forge, where also geophone data and conventional data are located. And this is an example of a magnitude -1 event. And you see that by looking both at the spectrogram here and the panel in the middle, and both on the PSD values, that DAS has a higher self noise than with respect to the geophone data. So this is just an example showing that DAS data actually is very, especially from the lower signal to noise ratio events and lower magnitude events, is very noisy, and so this must be addressed. So for this reason, we developed a spectral subtraction-based approach, which actually comes from the world of audio signal processing. So basically, this method was first developed on 1979, I believe. This was adapted and applied to DAS data. So let's start by first extracting, as an example, a trace, a channel from the DAS array. So as a first step, you will need to do a segmentation and windowing. So by means of a sliding window, and for each window of a user-defined length, you compute the Fourier transform to estimate the amplitude spectrum at first of a given number of segment that the user can define, where only noise is present, and then you repeat the same for the whole trace in order to estimate the raw signal spectrum. Then, since what you want to obtain is actually an estimate of the clean signal spectrum, what you did is actually performing this spectral subtraction operation, where you subtract the raw signal spectrum from the noise, from the estimated noise one, and then you go back to the time domain with the inverse Fourier transform and repeat this step for every other channel of the DAS data. So this is the main approach, basically, in simple words, let's say, of how this method actually works in principle. So you have already seen this slide from Professor Grigoli earlier. So I applied this method on microseismic data from induced seismicity data from Forge. So Forge is an enhanced geothermal system, and in this work we applied this method on this well here. You have two wells where DAS cable is installed. I applied this on this 70AB32 borehole. The data has more or less 1,000 channels, spaced 1 meter, and 4 kilohertz sampling frequency. So very high density sample. So yeah, this is an example of let's say raw DAS data before applying the denoising. You can see that I just applied a simple bandpass and FK filter to remove the K0 component, which I forgot to put a slide for this, but yeah, usually in DAS data you have this strong coherent noise occurring along the K0, the wave number 0 component, which is due to the interrogator vibrations, the laser vibration on the interrogator. And so yeah, this is an example of medium, let's say, signal to noise ratio seismic event before denoising, and this is after denoising. You can see quite an improvement. So if I do back and forth before and after denoising, you can see that also these other two events around 12 and 14 seconds after denoising are very much clearly visible and well detected if you run a detector that you saw before. I forgot to mention on the right you have this matrix where you basically have the signal, the segmental signal to noise ratio, which is basically a metric to see the improvement in signal to noise ratio before and after denoising, and is computed for all the segment and for each DAS channel before and after denoising. This is just a zoom in section around the main seismic event, the medium seismic event, SNR seismic event around 8 seconds here. You see that, yeah, before denoising and after denoising, extracted some traces, selected traces at different depths. You see that you get a nice improvement without actually without actually compromising, let's say, the phase of the actual noise, the actual data after denoising. Yeah, it is an interesting, another interesting case. This is a lower signal to noise ratio seismic event. You can see basically, actually, you can barely see something here around 3 seconds, but yeah, before denoising, this is actually the strength, let's say, of this method, that because that after denoising, you get a very nice improvement. So I do it again, before and after denoising, you get a nice improvement around 3 of this event, but also you can see other 2 events. So this is a very, very, very weak event, around 6 seconds. Here there is another one, and also around the 14 seconds. So the strength of this method, I would say that's basically if you just apply standard standard filtering steps like bandpass or the FK filtering, you still don't see anything. So you need something more, let's say, powerful, or advanced method like the spectral subtraction method here is working quite well. So yeah, this is again before and after denoising. I was a zoom in section, 1 second of the data around the main event. You see that before and after denoising get still a nice improvement. Yeah, after applying this method. So yeah, basically we applied then we applied the denoising method, this denoiser method on other 29 selected DAS data from Forge with a different SNR signal to noise ratio values, and you can see that basically you get a better performance. You get a better performance for regarding the lower signal to noise ratio values. So on the circles, you see the data before denoising, and on the diamonds here, the yellow diamonds, you see the after denoising. You get a nice improvement in signal to noise ratio, in the maximum signal to noise ratio. So before and after denoising, but also still on the medium has signal to noise ratio and higher signal to noise ratio still improves, the quality of the DAS data. But actually, this method, I show you only DAS data from Forge, but can actually be applied also to surface data? Yeah, the answer is yes. So basically, this is the Kefalonia data you saw earlier from both Emanuele presentation. This is surface data before denoising, this is just an example to show how this method actually works also on the surface data, so and also on 7,000 channels. So this is before, and this is after. This is before, this is after. So you see also the applicability of this method also in this different fiber optic deployment. So yeah, in conclusion, basically, yeah, we propose an effective solution for dust data denoising based on the spectral subtraction. We show that you can improve the signal tonicization of dust data, in this case of Forge, but also on the surface dust data. And yeah, as I show you just now, this method is effective in different fiber optic deployments, so both in boreholes or surface dust, or I mean, this here I just shown a Forge, which is a vertical well, but I've applied this method also on other data from I don't know, from a CCS site, for example, where the well was inclined, so with a dipping. Yeah, the fiber was in a, I mean, inclined well. I can't say the term exactly, and is actually a low has a low computational cost and a few parameters to set actually. So it's quite efficient, I would say. So yeah, thank you for your attention, and I'm open for questions.
Any questions?
Yes. Can you go to your second last slide where you show the surface data, that's data, your application on the space data? Yeah. So if you go to the noisy data first.
Yeah.
Oh, so the method is you selected two spectral boxes, and one is the noisy part, the other is the cleaner part.
Yeah.
So in this section, then where is the I guess the noisy part would be the top, then
yeah,
and
exactly.
then you pick another box on the signal itself, I guess. For instance, somewhere around channel 1500, and at 10 seconds, is that the other box where you define as clean?
For this case, I select yeah. Okay, so actually, as I mentioned earlier, describing this method works trace by trace, so channel by channel. So in this case, the channel are on the axis. Yeah, I forgot to because earlier here in Forge, I plotted in a different way. So the channels are on the y-axis and the time on the x-axis. In this case, it's on the opposite. But so yeah, basically, if you look at it like this, and for this case, I selected the noise spectrum estimation basically on the first 6 seconds of data, basically, and then yeah, it goes trace by trace and with us overlapping segments by means of a sliding window. So basically, yeah, you just need to select. Let's say the seconds, the time frames that you want your noise spectrum estimation, and then the algorithm will do I mean, will do the rest by himself. So you just select once, and then it's iterated over all the traces.
It would be interesting to see it on the application on reflection data, because then possibly you have the spectral overlap, and I wonder if it will work.
Yeah, I mean, I didn't test it on reflection seismic. I don't know if it could work, to be honest, but I mean, I would be also curious to see if it works. So yeah, I mean, it works on conventional seismic stations because I've tried that and it works quite well. But since of course, it's applied trace by trace. You can apply it, I mean, to whatever you want, basically. Also, reflection seismic, why not?
Thank you.
Welcome.
Please, those who are
Okay, thank you. It's good coming up with a model that would do something like this. And of course, we're in the world of automation. And now I noticed that for projects like this, the size of the data, most especially I worked on AVO sometimes ago, and the size of the seismic I used was just 29 megabytes. So it was easy for the model to come up with beautiful, fantastic results. But when it comes to real life, it's not like that. The subsurface data we get are always noisy. So I want to ask, what is the chance of this model being able to give us accurate results? Thank you.
So I don't think I got your questions, but I cannot hear very well. Could you repeat, please?
Okay, this particular project, you are able to use a model and to come up with a good result, a presentable result. But now I want to ask concerning real data sets in terms of volume and in terms of complexity. How good is this model?
So you mean how good is the method performance in?
Yeah, the performance, yes.
On continuous, let's say, in continuous data. You mean in terms of computational capabilities, or?
Yeah, in terms of computation and in terms of time. Yeah, time.
Yeah, at the moment we are working on parallelization, code parallelization for integrating this method in a near real time or let's say workflow, because currently this method, all the analysis that I show you, I applied it on my standard laptop, so with basically no, I mean standard computational resources. And if, for example, for the forge data, you have to consider that this section is 15 seconds, but it's sampled at 4,000 kilohertz, 4,000 hertz, sorry. So it's very high, sampling frequency is quite high. And in this case, it could process this 14 seconds of data in 1 minute. But this in this case, the data is not, the code is not parallelized, and I applied this on my standard laptop. I tried to run this on an external server, and this would take 10 seconds. No, sorry, 12, 13 seconds, something like that. So without parallelization. So I think that after parallelizing this code, and I mean, if you run it on a server with high computational capabilities, I think this method would be suitable for running in continuously in near real time application. I would be curious to do that, so then we are working on it. Yeah.
Okay, good. Thank you, sir. Thank you.
No worries.
Thank you very much. Please, those online, do you have any question? Thank you very much for your presentation. So our next presenter is Mr. Abdurrahim, a research scientist at the Center of Seismic Imaging at the UTP. He's going to share some of the work we've done on distributed atmospheric sensing.
Hello, yeah. Yeah, our head of department could not be. Can you hear?
Yes.
I'm presenting on behalf of our head department, Associate Professor Dr. Abdul Halim. Cannot be here. Unfortunately, he cannot be here with us today. But anyway, a bit introduction to the center. So we're more into subsurface imaging, but not limited to seismic, but also gravity and electricity, that kind of thing. But currently we are more into dust subsurface imaging as well. So this is the center backgrounds where the mission is to develop robust technology to image subsurface with greater clarity for better and precise decision making, and using, like I said, not just seismic but also SEM and electricity and geotube, whatever, but mostly seismic though. And this is our research program. As you can see, we're into many projects with Petronas and also other oil company like Total as well. So, and currently we're into CCUS, and also we are interested to some research on groundwater and geothermal. And hopefully, I don't know, there's also some students are working on mining, I guess. And today I'll be talking about one of our work using DAS, which is subsurface imaging. So this work was done by the center, so not particularly by me, but I'm just the presenter here. Okay, go ahead. So we started to, DAS is very new to the center. In fact, we only started to, out of interest, we acquire our own data at UTP, at this university, at the campus. But unfortunately, at that time, we don't have the resolver suite. So it's quite a short cable, considering it's only 120 meter cable. But we're using Terra 15 as the interrogative unit. Next. And this and for the source we use so active source /MO, because we have many young students, and also a mini vibro size, which has unfortunately a range frequency of 20 on the low side to 240. And the penetration there is just slightly, it's around 500 meters or so. And then on the fiber side, we have the ordinary fiber, and also on the armored fiber or the steel braided fiber. Right. And because we have a student who working on a helical cable, so he does it manually, but enough for the 120-meter cable, I suppose. And then we also tested on a single mode fiber and versus multi-mode. Even though actually for the multi-mode we should have longer cable, but this was done last year. At the time, we only have 120-meter cable. These are the summary of the data acquisition the data that were acquired. So we have single mode straight fiber, multi-mode straight fiber, and then a single mode helically wound fiber that was done manually. And also to compare that, we have geophone with 58 channels. And as a source, we like I said, we have both hammer and vibro size, or the mini vibro size. And for trace interval, for the geophone is 2.5 meter, whereas the dust is whatever the native of Terra, which is 0.816 meter. This is the basic processing flow. Basically, it's whatever that is applied to geophone. We try to apply it to dust and see if it works. So these are just standard seismic processing reflection seismic standards reflection seismic data processing. Okay, this is just a first look at the field shot icon. So on the left is the geophone. As you can see, typically a geophone would always be alias, and on the right is the dust straight fiber. So as we know, it's dust compared to geophone is the signal to noise is a little bit low, and on there's a small box on the right to show the amplitude spectrum. This is really the raw data set. And if you go to the next, and this is after applying 5 Hz low cut filter, and where we have removed the vertical lines just now. If you just put 2 input on, okay, and next is okay. These are just the normalized amplitude spectrum of the before and after low cut filter. And this is just to show the frequency FK spectrum of the geophone versus dust, where you can see, as expected, because it's layers, you can see a red brown in the geophone FK spectrum, and not so on the dust. Next is display of single mode versus multi mode, as I mentioned, because the cable is quite short for useful comparisons. So they are basically similar. On the right, small box there shows the amplitude spectrum of the single mode and the multi mode. So they're basically the same for this particular experiment. Next is our straight fiber versus helically wound fiber. So it's okay. The source is the mini vibro size. So I guess that's why I like the spectrum of this data, so where they are fairly broad compared to hammer just now. I said that because the source is starting from 20, we're living on the 0 to 20 Hertz. Okay. This is a summary of all the experiments. We have the hammer geophone versus hammer dust, and with vibro size geophone versus vibro size dust. So the main thing is that because, as we know, dust has more traces or more channels compared to the geophone. Of course, then it's not layers as compared to the geophone. But the downside is that the signal to noise is a little bit, but we can handle that. Next. This is the stack section comparisons of all the. Unfortunately, like because the cable is quite short, so that's you can't really make any sense of it. So, but like I said, this is our first experiment on dust. Okay, next, oh, this is another. We were this is another processing, surface dust processing that we did last year. But this data set was given to us by one of our sponsors. It's interesting. So on the far right is the red is the source, which is about 5 kilometers end to end. And then the blue line is the receiver, which is about 260 meters. What I want to show is, so this is the geophone data set. So on the left is the vertical geophone, on the right is the horizontal geophone. So you can see on the vertical geophone, there's some horizontal event, which you don't see it on the horizontal geophone VF. And if you go next, of course, in the dust also, because it's similar like the VS, you don't see the vertical or the horizontal event at about 0.6 seconds there. So this is, we think that the geology underneath at about 0.6 seconds, there's a flat event. So because dust is not sensitive to flat event, that's why it's not, and we see the same thing also in the VX. So now if you go next, what do I have? So okay, this is a stack comparison between the geophone VZ. So remember the 0.6 second or 600 millisecond data, that's where we have that red box there. You don't see that on the VX because it's missing, or it's not as strong as in VX. And similarly, if you go to the next slide to show the dust section. So, but in the helical fiber, because now we have some angles, so it's much better than the straight fiber. So that's one drawback with dust is that if you have a flat event, you're gonna miss. But we can overcome that with helical fiber. What do we have next? Also, some challenges that we, based on our experience at our campus, is that there's some cable coupling problems. Also, the fiber cables are very susceptible to damage. And that's I've shown with there's also directivity issue with dust. And so next year we plan to acquire data using a much longer cable, still not as long as I hope, but at least we want to get around 500 meters, if not 10 kilometers for better imaging. And also we need to dig a deeper trench to get better coupling and maybe use the enhanced cable to reduce the risk of cable damage. I think that's all I have for today. Yeah.
I'll start with the first one. Any question? Let's go. Okay, so now open for any question.
Okay.
So I might have a curiosity actually. So
okay.
yeah, what's you mentioned like for an next experiment, no? I mean, we want to dig deeper, as far as understood, to try have a better coupling. True? Is it true?
Yes.
Okay. How much deeper?
Maybe just 5 meters. Currently, it's only a few centimeters, right? So,
yeah,
or
I mean,
meter.
should be fine, few centimeters, 20, 30 centimeters. Usually, yeah, it's fine. Yeah, that case should be fine. Yeah, at least because those data are from Sorry, maybe it was you already clarifying during the presentation, but was with a fiber optic cable laying on the ground?
No, it was in about 1 meter.
Okay,
inside.
okay, sorry. Okay. And so you want to test different coupling?
But yeah, we think that if we do 5 meter, we will have better coupling, especially with the enhanced cable, hopefully.
Okay, yes. Yes.
Enhanced
Okay,
cable.
now I see.
I know. So we have last time we mainly use the ordinary fiber, which is the blue. So
Which is the interrogator? The Terra
Terra 15.
interrogator.
We also have new racks, and later next year we're gonna buy another one, I think. Yeah. Which is what is it? OptaSense, yeah.
An OptaSense. Okay.
Yeah.
Yeah, it's actually, at least for me, it's the first time I see this data from the Terra interrogator. Usually I see, data from, I mean, Phoebus, Sirixa, OptaSense. So interesting, very interesting.
Yeah, first time for us too.
What's the the range of this interrogator in terms of like a maximum interrogated length of a fiber distance? Sorry, if you know.
The maximum,
I think it's 40.
40 kilometers around there.
40. Okay.
40.
Yeah.
Kilometer.
That is me.
40, 45 meters.
Hotel, talking about there. Yeah, 40 to 45 kilometers.
Thanks.
You have a question?
What's that? Yeah.
Okay.
Any more questions?
Anyone?
Okay. So I think that's all. We would like to thank our colleagues from University of Pisa for taking the time to share their research with us. We are grateful. Hopefully, you can join next time. Thank you very much.
We have Dr. Halim over there. Maybe Dr. Halim wants to say something.
Dr. Alvin Johnson. Dr. Alvin Johnson.
Maybe not that.
Maybe he's in another meeting.
I think.